right, so on our last topic this semester, text mining. But here, I'm probably not going to focus on how good this technique is, even though it's definitely one of the most, the hardest skill to acquire at the moment. But here, we're more focusing on the underlying algorithms that generate, because it's a generating model, generate, or in other words, become the backbone of this text mining industry. But later, the virtual allocation algorithm. But before that, we're gonna, again, still going to talk about some of the very essential of text mining and what it is and what we can do about text. So here's our roadmap. Again, we're gonna first talk about what text mining is or not. Then we'll jump to sentiment analysis and also wrap up today's talk with some sort of exercises. It's a very, say today's going to be a very dedicated and also technically involved topic, and we're going to spend probably more than 2 hours talking about that. Unfortunately, and hopefully, since since currently we are experiencing another COVID spiral, so you would be hopefully you'll be staying at home and learn all this stuff at your own pace. So that's good. And I would start with topic model for next week, since we probably don't have enough time to talk about it. All right. So before that, we're going to talk about text, or simply the power of Word. So we probably heard about it, right? So Word is currently the single most powerful tool available to our humanity. We can choose to use the word constructively, I mean in a positive way, with word of encouragement, or on the other hand, you can choose to use negative word in a destructive manner. For example, like word of despair, right? That make people feel really disappointed, hopeless, right? It's because words have the ability and power to harm, to hurt, to humiliate, or in a positive way, to humble, right? So word is a very useful tool to our humanity, and because of that, people have long been aware of this potential. For example, can you skillfully structure text in writing, for example, like the article that you read, the news piece that they read, or even sounds that sort of like skillfully edited disinformation, or aka fake news, that you read elsewhere. Through this carefully structured text and word, and careful selection of word, they can influence your sentiment, right? And put disproportionate emphasis on a certain topic, and then tilt your perception to their favor. For example, like the ongoing Russian-Ukrainian war is one such example. People are more sympathetic of the Ukrainian side, or they also are more resentful of the Russian invasion, right? Also, some sort of like legislative pieces, or some single that launched by some single cause group or interest group, lobbyist group. They can carefully select more. For example, like, we should protect animal rights. See that those dogs or cats, they're so miserable, they be in poor condition. And then we need your help to for donation to help improve their living standard, living condition. Right? And then there's some carefully selected word like miserable or something like picture, and they kind of arouse your sympathy toward those causes. And also, more important than that, by analyzing text, you can actually infer entity relationship. For example, who's dependent and who has some kind of relationship with the group. For example, if you read like text about political campaign or financial donation by some certain corporation to a political candidate, you know that, oh, they probably have something going on. And probably something that's really inconvenient to tell, right? Or some group has some sort of hierarchical relationship between different groups. Also, you can also tell what's the topic, the main topic of this piece of paper, or this piece of information. So, okay, this topic is more about election, or this news is about COVID, more about COVID, right? Also, you can probably infer the emotion underlying those pieces of information. For example, if you see the atrocity of the ongoing war, you see that that feel those actors feel remorseful or sad, right? Or on the other hand, if you see that for example, this in just 1 month there will be our college entrance exam season. I'm not sure if I got this right, this date right, but anyway. See that, okay, so after months, and some student got matriculated into some really good college, and you can tell from the news report that, he's very thrilled about him or her getting to college. And you can tell the emotion from the piece of news. And to do that, we need to use some data analytical skill, like text mining or sentiment analysis to help us extract information from those raw tags. Here I have to emphasize raw tag, and you will see what I mean in a couple seconds. Also, we need to infer meaning, not just by reading those tags and then project it into the media setting and word cloud, right? We need to infer meaning from those text data in order to eventually tell the entity relationship, the underlying topic, and even the distribution of those topics in the entire corpus, and the emotion behind it. So again, here's our roadmap. So essentially, text mining is more about calculating large piece of text data, and then estimate the joint probability distribution between among the distribution of topic across document, also the distribution of word across topic, and their joint distribution. For example, what's the joint probability that you extract, randomly extract any word? Here they actually use a jargon called token, right? You know to write a solution like you put this on play. Probably if you are my age, you can play like those digital playground, and you need to purchase a token. You need to purchase the entrance to the playground. Okay. So they use a special term called token to refer to the word that is trapped on that. So what's the joint probability of if you randomly pick a word that from a document that word had a higher probability of being related to a particular topic, and then we estimate this relationship. But the first thing to know is that at the moment, computer cannot directly interpret the text. So I would say my only hope is that after you took this course, you take this course, and then eventually you meet up with a friend and say, I'm doing text analysis to have computer read those texts and tell me what's going on, and that's a text analysis. Then you can probably correct him or her. So no, that's not the way that we do text analysis, because at present, computer cannot directly interpret text. Instead, you need to import those raw tags. For example, you can actually do this in your Excel editor. I actually usually do that. I tend not to go along with those super fancy skill. I usually store tags in Excel or CSV format. Of course, but that can get a bit chunky if you have, say, billions of documents to analyze. But that's my way of approaching it. So the first thing to know is that actually you need to import those route paths into standard data format, and then label it, or to use some conversion skill or transformation skill to convert it into machine readable form, and that is you need to convert it into number, right? Annotated with some sort of meta information, for example, document ID, the relationship between different entities, and also the word. So you need to label each word with a number. You actually need to label them with each of them with a unique number, so that the machine can calculate the joint probability between, say, word I and word J, conditional on their some sort of relationship with other word, for example, word K, right? So that's how it is. It's actually not that the computer can directly get, okay, so this piece of news is about the presidential primary in the KMT party, and the first line of the text is more about the upcoming the U.S. election. No, it's not. You cannot directly tell, or maybe like in 10 or 20 years time, you can do that with the fast development of artificial intelligence. Maybe you may be able to do that, but at percent you can't. So, and of course, the data formatting, importing route path into machine readable form is slightly different depending on the content and also the language that are used. So here I demonstrate two methods. So the first piece of text about the U.S. election 2 years ago. The second piece of text is about the Taiwan presidential election. Again, almost nearly 2 years ago. Right? So you simply copy and paste that from some news, and then you just paste that on your Excel or CSV editor, just like what I did here. So that you can annotate it with document ID, and that's the tab, pure text, and that's the part of the information. Or simply, if you view it as some sort of data frame structure, and that's the data column that we will be working on. And then you can also annotate it with source. For example, it's definitely found MSNBC. I think this is the most news source. And this one, Yahoo Taiwan, and also you can annotate with date in case that you want to plot it, the time trend of the popularity of some political candidate. Right? So here's the first stage. And then, as I said, we'll just cover second skill. This column is what we will be working on. So we will need to apply this following preprocessing skill. Here, preprocessing task to turn down this pure text into machine readable form. So the first skill is parsing. So what's parsing? Parsing is simply a process of breaking down a text into its component part of speech. So if you took say text mining, if you took say more advanced text mining courses, you were running into this concept of part of speech. So for example, if I say I love you, the I is the entity, right? The love is the verb, you is the subject, right? So each piece of text actually have different part of speech, right? And in order to do that, we need to remove the punctuation because, well, they seldom, I wouldn't say never, can be a clear indication of the meaning of the text. And also bracket, right? But of course, in some analysis, bracket is very important because bracket is when you want to emphasize something. The special symbol, like for example, like nowadays, that younger generation, including myself, they actually use emoticon or emoji a lot. And That's good because well, if you simply look at the emoji, you can tell the state of the emotion of the person who sent this message. But they can also place additional burden on text analysis because if someone purely someone just use emoticon in lieu of text, and that actually is occurring emotion harder to analyze. Oh, by the way, do you know how a machine reads those emoticons? Well, actually, each emoticon if you look at this underlying programming code, its meaning is that enclosed in a square bracket. For example, you say smiley face. Something like this, right? And then this is how you look like in your message if you're a human, if I'm looking from the perspective of human. But if you're a machine, then this is what would be read into the machine. So they enclose the expression, say in text form, inside square bracket. So if you after you encode it and then send it to the machine, you will simply decrypt it, decipher it, and then remove the square bracket and read directly from what's inside the square bracket. So, okay, so that's an expression of joy or happiness. So after that, we'll go to STEMI. STEMI is simply a process of reducing word, because even for the same word, they actually have different mode of expression, right? So they're reducing this different type of expression or a time usage to their base root form. For example, you will need to remove those effects, such as, for example, the past tense when you use the word in past tense, or in verb form, when you're doing something, or third person singular. Where's my? For example, we just use the word remove as our example. Say, for the common root form is remove, right? It's most basic form. But if you use past tense or something in a more subjective tone, it's say remove, right? Well, they probably confer the same meaning. Right? Or third person singular, say he removed or she removed. Right? So simply who does that? Right? So it's simply reducing those different variants of the same word to its common root form. Just like this. It can be also be applied to other terms, for example, adjective or other, for example, like verb, or even the word in its plural form. For example, cars, or in procession, cars, right? Or processing. And the third process, called lemmatization. Even doing some text analysis, they actually do not apply the scale. But it would be worthwhile to explore that, because we're actually some word actually confer similar meaning. For example, if you watch those Hollywood movies a lot, you can see those like police movie. You see like two agents are driving a police vehicle. They have a special term for this vehicle. So let's just use car as an example. It's a car. Another term for car, maybe a more generic term can be vehicle, right? And you're probably seeing two police officers, two agents, FBI agent, driving a car. They say, oh, that blue vehicle looks suspicious, and we are chasing it down. So vehicle, car, or automobile, they refer to the same thing, right? For example, you say missile, rocket, or projectile. They also refer to the same thing. Right? So we need to use lemmatization. So lemmatization is a process of grouping together methodologically similar, meaning that they are similar in meaning. So they can be analyzed as single item. So like analyze a tab, for example, that repeatedly that shows that vehicle, car, automobile. So you wouldn't treat it as three different subjects, and then incorrectly infer their correlation with other text. So you're simply reducing it to a single term. Then after that, you simply collect it into a big corpus. So corpus is the large body of word term. And sometimes in text analysis, if you're working on some example data, they simply throw you a piece of data called corpus. And then it has a large collection of all this preprocessed text. Meaning that they have already done this for you. And you simply apply those text mining model on the corpus. But if you are required to work on some raw tasks where you collect those tasks on your own, and then you need to do all this yourself. But of course, as I said, there's some differences in terms of how we process those tasks. It's written in different languages. So I just use one example. Now, the problem was processing text in Chinese. So you probably heard about this person, right? So our former Gaussian mayor, who been deposed 2 years ago, but for a reason I don't know. So he was handpicked to, well, he actually won the primary, right? So try to reconnect you to the synchronicities. The primary, on the KMT primary, so he ran against the DPP candidate, current President Tsai Ing-wen, but eventually lost, right? So, but he became really sensational between like 2019 to 2020. And if you do text analysis, simply search his name as an internet trend, you see that he kind of his popularity experienced a spike between 2019 to 2020. But if you want to do some text analysis on that, simply by searching his word in Chinese, for example, on Google or Microsoft Bing, then you'll find out that his word, his name is somehow related to a physical exercise, to yoga. Because in Chinese term, so this is probably shouldn't call it as a problem because because it's just a different way because it's just the way that you write Chinese. Because all the Chinese expression or word, they are connected together. For example, they say, I love you, right? In English, right? The sentences only consists of 3 words, right? So you can simply parse them out, right? And because English texts are separated by space, right? But in Chinese expression, they all connect together. So if I simply translate the sentences to Chinese, you say, they're all connected together. So you can throw that into your text processor or text mining algorithm. Your algorithm will have difficulty about where should I parse the sentences. Try to treat this first two texts as a single term. And then give it a label, say as a word ID. Or should I treat the last two characters as a single term, and then assign it an ID, say word 2. Okay? Or simply treat the 3 characters as a single word. Of course, I mean, from the standpoint of a native speaker like you, to say, oh, this is so easy. But I mean, you have to put yourself in the shoes of a machine, right? You wouldn't be able to tell. Also, let's come back to about the meaning of his name. Because the first 2 words, if you simply grab the first word and treat it as a single term in your machine, your machine, then its direct translation is just Korea, right? So if you were doing text analysis 2 years ago, focusing exclusively on American Yu, you will find out that a lot of his news are somehow correlated. If you simply apply directly those probability-based machine learning the text mining algorithms, you'll find out his name is correlated. It's probably due to some spurious correlation. But anyway, you'll find this strange trend that his name is correlated with Korean or Yuga. That's meaningless because he certainly confessed and is publicly that he practiced yoga. Oh, he probably practiced yoga, I think. But probably had nothing to do with Korea. Right? It's because your text mining algorithm had difficulty about where to parse his name. Right? So I guess the best way to handle this situation is simply you need to annotate his name, and then ask R to treat it as a single term, or something Python importing Python, and then you should be able to identify that. Okay, so let's treat a single term. So its correlation with other terms should be calculated different. Okay. So after we've done that, we can convert our process, this clean, after you apply all the skill, into a so-called formats called the so-called document term matrices. So if you look at this Excel sheet, then you should be able to tell what it means. For example, the first column is document ID, right? And the second column is our preprocessed consists. So let's say each row of the second column consists of a token, or simply a word that's being preprocessed and extract from the raw text that we put into the data, right? So you see that the first document is just look at the document ID. The first document consists of multiple text or token, right? The Democrat that House Intelligence Committee, blah blah blah. While the second document also consists of multiple text because you kind of wrote because you had preprocessed and cleaned the text and then rotated vertically, right, from horizontal to vertically, and project each of the preprocessed token or word into its own row, right? So you can expand the dimension of the data. And then you calculate the total frequency of this term. So it's also called the document term frequency matrix. Right? And as you can probably tell, if you have a big chunk of data, say you have 1 million news report regarding the election of COVID, and then you preprocess the data and convert each piece of text into document term matrices, you will get a huge so you would get a high dimensional data, a huge data, right? And that's when the text mining is something get really intractable. Right? Of course, frequency can be misleading. You say, oh, so I would say the most important word here, that is judging from this picture, is the. Right. I guess that anyone can tell me that, but that's definitely meaningless to tell you this. Right. So here I'll offer an example here. Here's one example about it's a bunch of scholars who work for the Bank of England, their central bank, the central bank in the UK. They use text mining to study the board director's monetary policy, for example, interest rate, how to set the mortgage rate on the security related product. So the monetary policy. So they simply analyze the board of directors meeting. So for example, like what do they say, and what topic do they discuss during each meeting. Okay, so they have done all this and preprocessing and then projecting those preprocessed token into the media savvy word cloud. Oh, they found out that the most commonly used token, the word is the. Okay, fine. That's still meaningless because it's a commonly used determiner in English text, as you know. But it conferred no special meaning regarding the context under which the text is used. Because for any type of name, any piece of information, you find out it's definitely the most common determinant in any type of information. For the subject of your study, the central bank's monetary policy, I guess a more important term should be the policy, bank, or interest rate, because those are the terms you wouldn't be able to find elsewhere. And they are exclusively, because they're more related to bank policy, to banking or finance, monetary policy. So therefore, so for text analysis, we actually want our algorithm to tell us those more context-specific terms in order to help us infer the topic of tell. I mean, for context specific, for words that only or are more likely to appear in certain contexts. For example, if you find a word like howitzer, missiles, casualty, that's more, so that means you're more likely studying text related to war, military-like conflict. And for interest rate and banking policy, there should be more something related to finance or monetary issues. Okay. Here, I'll offer one example. Not sure if you guys watch opera. So I guess say after the COVID, if you went to the New York City, then you should definitely go through one of this. Here's one term. Probably one of the longest word in English. Say supercalifragilisticexpialidocious. This strange word only appeared in the opera, but it's been readapted to movie called Mary Poppins. So you can quickly this out. You probably wouldn't be able to find this word anywhere else other than Mary Poppins. So if you find out that okay, this word appear with high frequency in certain piece of text, but not anywhere else, then you can definitely tell with almost 100% certainty that that piece of text is Mary Poppins, is related to Mary Poppins. So in order to tackle this, you can use a scale called turn frequency, inverse document frequency, TF-IDF, to adjust the weight of the turning of text. So it's calculated as the turn, so a specific turn, frequency in a document over the total word frequency in the document. So total frequency, right? It's a turn frequency in the overall document. So you know that okay. So if that word appears now, that means that's equivalent. No, you need to again readjusted by the log transform total document and document with that contain this term. So you essentially scale down its frequency, meaning that for another document, this word so that the second term of this multiplicative term is an inverse function or decreasing function of the document that contains this. That means, well, if a word tends to occur a lot in certain type of document, but not in other type of document, that means that word is more related to a particular type of document, but not for all other type of document. So it's essentially used to identify the relationship between a particular tag, even though the tag is commonly used text, and specific type of topic. So that's how it was used. Okay. So we're going to have one example of that. So here, jump to our workhorse model in current text mining. You probably heard about this quite a lot. About topic model. In some textbooks, it's a generated model estimated from LDA. You say, what is LDA? Because it can be sometimes misconstrued or mistaken as other classification model, like latent discriminant analysis, even though they cover some object, but they are not the same. The underlying algorithm is not the same. So here is our workhorse model for latent differential allocation. So latent differential allocation is a mixed membership model. So you might get a little confused at the moment, but you'll definitely get to it in just a couple of seconds. It's a mixed membership, meaning that a word or a term, a document that can be simultaneously related, that mixed membership, to multiple topics, right? Meaning that, for example, a document can contain word, right? Because a document is just a text string, where the basic unit of this text document is a word. But the word may appear in multiple documents, right? So you have multiple membership in different documents, and a document may be related to different topics, and so are the text within those documents. They may be used in different topics, all those with different proportion, right? And also, a single document may cover multiple topics, so that all the constituent concepts, they have multiple membership across different categories. So this is what makes member generated model that group set of data to unobserved, meaning that they are unlabeled. So it's essentially an unsupervised learning or unsupervised classification algorithm, meaning that they do not have a hard label, hard clustering. Or sometimes they do. For example, if you analyze like the word or common usage of term in two distinct novels, which we are going to show. I'm going to show you one that exercise. So now you know that okay, they come from two groups. So that's what's it? Some sort of supervised learning, but not unsupervised because they actually had a hard label. Based on the similarity, or simply the joint probability that they appear together. And the goal of applying this model is that given the corpus, that's the collection of text, right? The data, annotated with additional detail or metadata, we can infer the underlying topic that explains any of the document. according to the generated process. The generated process is the process of estimating the joint distribution, the joint probability distribution of document, topic, and word, called the generating process, because that's the probability of generated from this supervised learning algorithm. And we use that to uncover the latent topic because, well, they do not have a hard label. The latent, so all of them are latent. They are now clearly specified in the data that are given to us. Well, because also because we collect those data and we do not have the hard label attached to it. Looking at text data. It's because the document may contain multiple topics and the word may be related to, it can be used in different topics. So they have mixed match. For example, here I offer you one example about when a single document may be related to different topic. So here's one of the Yahoo news that I saw 2 years ago. It said, well, so because at that time, you say, one half the world population are in isolation, whereas probably in the early stage of the COVID. So there's a news while at the same time, the US election is going on, where you see the economy is slumping. Right? So they had three things going on. It says the strength of the US economy will prove to be a important factor with voter head to the poll in November 2020, when the US voted cast their vote on the upcoming presidential election 2 years ago. According to US Treasury Stephen Mnuchin, they talk about financial policy, or physical policy, right? About economy, physical policy, they're probably related. Amidst the backdrop of the coming election, electoral politics. And the last sentence said, despite the anticipated cascading economic impact of coronavirus outbreak. So you revert back to the COVID and talk about its economic impact. Right, so you see that there's a bunch of interrelated topics in just a short piece of news. So even a single piece of news may cover multiple topics. Although they definitely the piece may actually allocate different proportion to each of the distinct topic. You see that economy, because you actually can found Yahoo Finance. So economy actually constitutes a larger proportion of the word and concept used in this piece of news, right? Everything, including the electoral politics and coronavirus outbreak, are related to economic. They emphasize economic impact. And so economy probably constitutes a larger proportion of the text used here. So here, I'm breaking down LDA to its constituent unit. So we're doing topic modeling. There are three components that you should pay attention to. So the most basic element is the word. In some texts, what they call it term, or simply call it token. But remember that token is the preprocessed word. But here, the word term can have many forms. Plural form, third person singular, or as a transform form, for example, verb, past tense, something like that. And usually, when you're giving the data, the basic unit of observation meaning that the row in your data is usually a document, a piece of text like this one, and which consists of multiple words. I'm plotting this to help visualize this concept for you. Here is the document, right? Document may consist of multiple words. And they are both document and Word, they may be related to different topics with different probability. equal, say, topic 1, topic 2, topic 3. It's something to say that if the list of words shown here, a commonly used term, then you can say that they probably all appear across all three types of topics, although with different proportion, and hence they're translated into different probability. You say that, I think so, for example, you can say the first word is probably, let's say, 90% of the time they are related to topic 1, and only 15% of the time related to topic 2. And 5% of the time related to topic 3. And document 1, you can simultaneously cover the first two topics, and document 2, you may cover all the topics, all those with different proportions. So you may cover topic 3 a lot, slightly touch on topic 2, and probably 10% of the word you use cover topic 1. So here's the negative things. And our task is to calculate this joint probability distribution between topic and document, the word and topic, and the joint distribution of word of certain topic when drawing from any of the documents. So that's. But technically, the Dirichlet distribution, we just remove the adjective latent Dirichlet distribution because it doesn't have a string label. It's latent. But in itself, the Dirichlet distribution is a conjugate prior of the categorical distribution of the multinomial distribution, like this one. In a multi-category, right? So it's exactly what we are doing here. And an infinite dimensional generalization problem of the Dirichlet distribution is called the Dirichlet process. For example, if the Dirichlet distribution is a family of continuous multivariate probability distribution surrounded by the vectors, so here the vector alpha is just the topic distribution across different documents. In some real value space, then a real positive value space, because the probability cannot be negative. Also, it has to be larger than 0. So we actually mentioned this when we're talking about the Bayesian probability a couple of weeks ago, right? I said when you enter into an ice cream shop, suppose the ice cream shop offer 200 variety, 200 flavor, 200 different kind of flavor ice cream. The probability that you will purchase any of the flavor is strictly larger than 0. It cannot be 0, right? So, well, because the reason that the ice cream shop offers is because someone had purchased it in the past, right? Only with close to 0 probability, but it cannot be 0, and it has to be larger than. It has to be larger than. It has to be some positive value, and it definitely cannot be negative, right? So the Dirichlet distribution are commonly used as a prior distribution for Bayesian statistics, especially when you are analyzing a count model. So in Bayesian probability theory, the posterior distribution and prior distribution, if they come from the same probability distribution family, then we say they are the conjugate distribution, and the prior is just the conjugate prior for a likelihood function. It's an underlying parameter, the model parameter conditional on the data, so given the prior, and normalized by the probability distribution of the data. So the probability of all outcomes, say here, all type of outcome that we draw a word that is of certain topic, right? It can be any of the topic from the given document. It comes from a collection of vectors, and the sum of all this value must equal 1. Right? You say that. Say if you simply draw a word that can be the first topic, or the second topic, or the third topic, but its cumulative probability I have mentioned this when we discussed low improvement model. Cumulative probability must be 1, right? It has to be either one of this, right? Either one or multiple realization of this, but the cumulative probability has to be 1. It can only come from this simple space, right? Also, none of this can be negative, as I said before. You cannot have a negative probability of purchasing any ice cream flavor. Because I really hate that flavor. I would never buy it. But you cannot have negative probability of purchasing, right? Because the realization of the probability that a word or term 1 is of topic 1. You can say it's close to 0, but it can never be something of negative value. So it cannot be negative. And so this cumulative probability is 1. Has to be 1. So I'm showing you this. Okay. So if you visualize it in the data frame structure or something in your Excel or CSV spreadsheet. So suppose the row is the document ID, the column or the topic ID, and what's inside their intersection or in each cell is the distribution of words. So it may consist of multiple words, for example, like word 1, word 2, word 3. Okay. So here we can directly count their joint probability distribution, or simply show you the distribution of topic across document, also the distribution of word across topic in the document. So at the top of this page, you see that, well, since in document 1, the 10 words used in the document are all related to the first topic, topic A. So that topic distribution, the topic is close to 1. It's all clustered around topic A. But for two other topics, it's just close to 0. Right? The same for document 2 and 3 as well. Now you see that here, the term used in document 4 are evenly distributed across the 3 topics. Right? So the term distribution across topic in the document are more evenly distributed. So you see it's simply divided as like 3. So that the lower the B, the more dispersed term distribution across topic in the document. Also, you can use that as the probability, which we term as alpha, for the topic distribution in the document. See that, okay, so the 3 topics are also distributed evenly in document 4. But for the first topic, for the first document, the distribution of topic 1 is just 1, because this only is just 1, right? Document 1 only has 1 topic, right? So it's close to 1. So how do we begin the LDA analysis? Well, as usual, before you begin, you need to preprocess the data. Also, you need to set the term limit, because some of the term, if that appears less, or maybe just once or twice, so the ceiling occurred in the entire corpus, then you might want to simply remove it or discount it, because that would place additional burden on text analysis. Because if you need to look at our slide from the page out, you see that, okay, because each term will help expand your data, right? So we can increase the dimension of your data, which will make our analysis intractable. So we actually don't want that. So we usually want to set a meaningful limit, text number limit, the frequency limit, about on the criteria that the text would be included in your analysis. For example, you said, well, you can use maybe like 50. So if a term that appears 50 times in the entire corpus, then we should include that in your analysis maybe 200 times. But if that only appear like 5 times or just once, only appear once in the corpus, then you can just throw that out. Right. Then determine the number of topic. We will get to that in 10 seconds. No, in 10 minutes. But it wasn't really saying to set out the distribution of topic across document here, and distribution of term per topic, the data. Right? And as I show you, higher alpha means that the topic are more mixed. Or lower, or also if you have more word cluster. On the other hand, if the distribution of term across topic are more dispersed, then you probably get a lower data, right? They're more dispersed. Well, if the topic is more concentrated in a particular document, then you should have a higher alpha, right? But here we see a lower alpha because topics are more evenly distributed in a single document. And then you use this information to construct a document term matrices, which I already showed you. The first column is document ID, second column is the term, right? So each document ID should map to multiple terms within the document that you extract from the same document. And also you might also annotate with the frequency with which it appears in that document. So you become document term frequency matrix, and then use the information from beta to construct term topic matrix. And so the first column should be the term. Okay. So the font times the guy really correctly, yes. Term topic, which saves us space. Term topic matrices. So for each term, may be related to multiple topics, right? With different probability. So you can say it's more associated with the first topic, which is 0.95, 0.0. It's also associated, but less associated with topic 3, but it's least associated with topic 2. Right? The same for the second term, W2. And then you can also expand it by the topic and then map onto its estimated distribution of term per topic. So, right, so each topic can be mapped to, each term can be mapped to multiple topics with different probability. So that's the term topic matrix. You can also do document topic matrix. This just this correct data. Here is just data matrix. The same document can be mapped to different topics. You can also count your underlying probability. So we're going to use all this parameter to calculate the joint probability. on the differential allocation. So we have, let me write this down, help you help myself remember what I mean. So alpha is the distribution of topic in document. Beta is the distribution of across topics. We also have DTN, which the fall invented here. We also have term topic matrix with part pi and a document topic matrix data. So you should probably know this and this. They should appear together, right? Distribution of topic cross document topic matrix, right? So this is used as the data, and this is the probability. Right? And this should also appear together. Beta, the distribution statistic, given the data, term topic matrix. Okay? And then we use that to estimate the LDA. So given alpha, the distribution of topic in a document. For each row of the document topic matrix, right? We sample a topic based on a probability in a row. So each row represents the probability that a document belongs to or is associated with a particular topic, right? So this is the underlying probability, the distribution, and here's the data. And simultaneously, we also need to estimate the term distribution cross topic. So given topic distribution here, after we get this, the topic for each term. So what's the probability given theta, given topic distribution, what's the probability that we pick a term from the document? The term is associated, or you can say the term should be clustered belong to probabilistic, a certain topic. And given these two information, we need to calculate the probability that if we randomly sample a term, right, from that has a particular topic, what's the probability? So that, you can simply look at here. The distribution of term across topic is regulated by beta, right? Distribution of term across topic. So we still need the data to estimate that. So what's the data? Term topic matrix, right? Each term is probabilistically associated with multiple topics, right? So that each row in this data is a term topic combination. Is determined by the probability beta, right? So given all this information about the probability that we pick a term that is of a particular topic from a document, simply estimate as this, the categorical distribution, or is it a multinomial distribution. And then for each term in the document, and for each document in the data, we simply repeat the above estimation process. But happily, unfortunately, we have a computer to do this iterative job for us. We do not need to calculate this by our hand, which is good. And because that can be tied to SUNY, so the LDA, if you look at the original code, letter C, by the author David Bly, they originally used a process called they originally used if sampling. It was much faster because you sample each of those parameters by assuming the value of all the parameters as a fixed, and then you iterate across the range of value through different combinations of values. So it's called a full conditional distribution of all the parameters. So it's simply taking all the parameter value as a fix, and then simply estimate one of this, and then do this multiple times. So distribution, all the parameters are just a conjugate prior for a particular parameter, and the full conditional of this test simply written so this last equation. Simply want to estimate probability that we pick a particular term that is a particular topic in the document. What's that probability? So that probability is realized as a joint probability distribution of the term topic distribution, right? Your immediate friend. And document topic distribution. And lastly, the term distribution across topic, across document. This. And give it a full conditional task. So to estimate that, we simply just to provide some value, assuming all the parameters as a fixed. And then to estimate each one of this, and then for all as well, and then fit into this number of document and number of topic, number of document, number of word into the model, and then the model should give us the estimation result. So, but I mean, at this moment, you should know that okay, so that's the number of document is something I know because we're simply looking at the data. I can directly tie dimension that then in my data frame. I know that how many documents I have, right? And also, I should also I can also infer by simply taking a look at the data, see, all right, so some of the documents are empty, and I should just use the MA omit or hour scale that I have acquired so far or printed elsewhere to remove those empty cells. So that should probably make my analysis much faster. So that's some information I already know, right? And also applying those parsing stemming levelization scale, I should get a list of token or a list of word, right? And then I can count the total frequency distribution and how many of it. So I should also know how many words that I need to tackle with, right? So that's the information I can obtain, right? So now I already have two of them. But what's the K? How many topics are ideal for my analysis? Well, there are two criteria that can be used to select number of topics. The first is fact-based. For example, you're giving 100 documents, right? 100 row in your data frame, and the person who give you the data, or if you look at the menu, you say, oh, they come from two novels. So you know that the K equal 2, right? That's just hard label. Right? Or there are some scientific way, numerical-based or statistical-based method that will calculate the quantity of interest and then plot it as a sort of elbow plot as a decreasing function of likelihood of correctly sorting the unseen document to the correct category, the correct topic. And that will require, even though it's scientifically calculated, that will require some eyeballing, meaning that it's you that need to make the decision. So a common use approach is simply to assess how good the LDA model you specify is adequate for identifying the probability of a word term appearing in a topic, or that's quantity of interest. Given the distribution of word in the document or the distribution of topic across document, as a function of the number of topics, something that we want to estimate, or something we want to know, It's simply done by the technique that you should be really familiar at the moment. By splitting the data set into two parts, one for training, one for task, and it's evaluated by the log likelihood of the train model as a function of turn topic matrix and also the distribution of topic across the distribution of topic in document. On a set of unseen document, that's something that you know, but that you do not know at the moment. So essentially, you use the train model that's useful for classifying the turn, the topic of the turn drawing from a document. So you apply the model that you train on the unseen document, see that if you can also correctly sorting the turn of a particular topic into its correct, most likely topic. So that higher likelihood would imply that, oh, okay, so the K is adequate. The K that you assume for this model is adequate. So you apply a better model, or simply a better assumption of K. And of course, you definitely do not just want to look at the number, right? So you want to actually plot it out, right? So you can compare that visually. So we can assess to what extent this model increase in K starts significantly improving the predictive power of the model, so that we shouldn't further increase K for, say, the existing number of K should be enough, and one additional K, say, maybe for any number of K beyond 4 is not necessary. 3 should be enough for grouping existing term into their corresponding topic category, and 4 is redundant. So we should not follow increase K. We should stop here with the measure called perplexity. So it's something called perplexity analysis. So which is simply plot as a decreasing function of the log likelihood of the unseen document, and the likelihood function you defined previously. So that the lower perplexity, the better the model. I can plot this out for you. So you should see it as a decreasing function of the likelihood function that you draw previously. Right. So that the lower likelihood, the better the model. But however, as the likelihood curve begin to flatten out, or even begin to increase, meaning that inverse function. Begin to increase, meaning that the additional K, so here the x-axis is the K, no longer significantly improve the model because it no longer help reduce improving the likelihood of correct topic assignment of term that you draw from the document to the most likely topic. And then, for example, at this range, we just see, okay, so that's probably the ideal number of topic that we should use for our topic model. And beyond this range, not necessary. We should stop here. Okay, so let's do a bit of R exercise before we proceed to sentiment analysis. All right, so for the first task, since we want to stripping raw task. Before that, we need to analyze 4 example tasks. So those are the news that are drawn from Yahoo US website. So you can actually play around with that, or simply using your own. So you can just grab any number of English-based news, but I have to emphasize that the skill cover here only good at analyzing English text. But if you want to analyze Chinese or Spanish or Japanese text, then you should probably consult say other example. Right. So concact them into a vector, right, using our familiar function, C function. And I create them into a table object. That's why I use the tidy in table. So that all the text element inside it are our factor class, which is useful for further processing because, as I said, R, or your computer, let's just not say R, computers cannot directly interpret text, right? You need to convert it to numerical format, but before that, you need to first convert the text string into factor, and then after that, use factor to map onto some numerical value. You'll also see that I'm going to include line number 1 to 4 because we have 4 pieces of text. So each document ID is mapped to the text string. So if you type this on your R screen, your R editor, see that, okay, so we have 2 columns. First this line number, or simply your document ID and the text. Okay, so here, say, wow, it seems that the preprocessing is really hard when you need to understand all those English grammar and have to find out this punctuation single space. Will that take me a lot of time? No. I just invoke the unasked token, right? As I said, the most basic or meaningful unit in text analysis is a word, which is called token here. So you say unasked. The nested means they are connected, and unasked means they're breaking them down, right? You say unasked the text into word. So you just use the pipeline function from dplyr and then unasked text into token. And this will break each token from a string of text and then create its own row. Right? You see that you actually transpose this vertically, right? So that each unasked token gets its own row, which is mapped onto its original document ID. Right? Very simple. You also remove the space, symbol, and punctuation directly for you. So now you're having familiar with this process. So we will work out an example from Jane Austen. Anyone know Jane Austen, the English novelist? Right, she's most well known for writing, the life of this gentry class woman living in the countryside about their relationship between other women and their men. Right, so the most commonly used. So I want to analyze what's the most commonly used word in Jane Austen's novel. You should probably just take a simple guess. An educated simple guess, you would tell, okay, so they probably use a lot of men, right? Female English men. And some object, and probably some terminology related to country life. Right. So we will also need string our package. So there is a data code original book. So we, there's a data code Austen book. There's attached in Jane Austen package, Jane Austen art. Someone already sorted for this. So we use pipeline function to ask R to group all of this data by books, right? So that within each book, group by means, okay, so they group the following analysis by book. So that the following command that we enter would be executed with by book. So that you would get this classification result or numerical calculation sorted by book or by the unit of analysis that they want. And then we create, means mutate, that create, and also append to new column called line number, and so the chapter name. So chapter here is just a regist, a regular expression. Use that to identify anything that that goes after the word chapter, right? So you will automatically detect. So you would probably return us a number, right? So string detect. So that we can sort this by book, and so by line number, and also by chapter. So annotated with additional information, for so line number and chapter. Also, we also tell all that just disregard whether those words begin with capital or lowercase. We don't care about that. And then ungroup convert it then back to its original scope. So that we got two additional column, right? And then we can check out our output. See that those are meaningless, right? Those are just punctuation, quotation mark. Then we can use the skill that you already know. It's unless token to remove all those, right? Those nasty things. Now it's definitely cleaner, right? So we have line, chapter, and word. But of course, some of the words are meaningless, like the and the, right? So what should we do? Those words are usually called stop word in English. And for here, you do not need to do much about it. We can actually call a predefined stop word dictionary as headed and already provided by those text mining analysis. It's called you just call stop word, data stop word. So you need to call this existing data specifically and enclose that with a function called data. And then I will look for it. So use nt join. I think I haven't demonstrated what is nt join here because when you're working on data, when you're working on multiple data, if you want to merge them, there are a couple methods to use. For example, there's an auth function that I personally use a lot called merge. And then you specify what is to be merged on, right? The original data set and the data set that you want to merge on it. So data set A, data set B, and there is another argument called by which column, so long as they match, then I will merge. But we can definitely set up other conditions. Say, well, if it meets certain conditions, say, well, if the name, say, you want to merge people's last name, so you supposed to work for criminal investigation, you want to investigate the perpetrator's name or the sex offender, so you want to merge their last name. So they have to be, you got to have the same last name, middle name, assuming that you work in the US. And want to place some additional conditions. You can use like inner join. Say, so the data is so the data that you want to obtain will only join the first data so long as certain condition are met. Right. So that some of the row in this data will probably find no match because it's conditional. The join is conditional. But on the other hand, anti-join means that if certain conditions are met, and then the element inside the first data will be removed. So we simply use this method to remove the stop word that appear in the stop word list, so long as some of the term in the certain column of data frame, or so the data frame object or table object of the data object A that met this condition. If they match, then they will be removed from object A. And because we perform this function, right? So you work on existing table object. So you need to create a new object. So that's why I put this here. Remember, you need to after you've done this operation, you need to generate a new object, right? You should not just, okay, I plotted it, and now I want to show how it's done. So without creating a new object, so just display this on the screen. Say, hey, why? Say a string, because I follow your R code. It seems that those things are still there. Those punctuation bracket space is still there. Am I doing something wrong? Yes, because you need to create a new object preceded the original one. Okay. Integer. All right. So after that, we'll count the frequency of the term that appear in the document. This can be easily done by calling deploy as count function because it may be masked from a similar function. This is a function of exactly the same name, the other package. So we need to use this to column to emphasize that this function comes from deploy package. I think I already demonstrated. Right. And then we want R to sort this by their word frequency. So I say, set the sort argument to true. And then I can plot word frequency. That's very easy. Just connect the previous function that used pipeline to use filter. So those that appear over 600 times or be retained. Others will not appear in your data, even though they will still be in the same data frame, the same table object. And then I create additional column code word by order by the number frequency, and I plot and send all those using pipeline function to ggplot2 to plot them with the word as the original or as the original x-axis, and the frequency as the y-axis. You say, oh, that's not what I saw, because the word appeared on the y-axis, but the frequency on the x-axis, something wrong? Yes, because I haven't mentioned the coordinate flip. Because if you remember the email that I sent you a couple of days ago, I said there are a couple of ways to render the plot in the way you like. Because usually it's a more intuitive way to look at a list of terms and their frequency in the horizontal version. Right? So we use coordinate flip to flip the original coordinate or original axis, so that the original x-axis, which I said as word, will appear on the y-axis, and their frequency will now appear on the x-axis. Right? Also, I can set the black and white scene. Right. The third task that we want to do is to compare Jane Austen's novel with another English novelist, so H.G. Wells. Anyone heard of that? Of course, I would not get any response. She was well known for writing the science fiction at that time, the late 19th century or 20th centuries. So you should probably tell that, okay, so he probably used another sci-fi term or a term that's dramatically different from Jane Austen. So let's compare that. So again, we apply the same skill to parsing, stemming the word by H.G. Wells. Right? And then we also count the number of frequency which those words appear in his novel. And then we convert that into a plottable object by creating a list of words, also annotated with their author information. So we create, so we simply bind the two rows to increase our data that we done previously for these two authors, and then we and from those data, we also create additional column that detect the word, simply the word, but not chapter or line number from this two source of data. And then we count them by author. So it's similar to group by, right? So something by author and also the word they use. So the final data will somehow look like this. You get to check this out by typing those elements and creating on the screen. Here I'm not showing you because they're extremely long. So you will have an author column, which I use the function called spreading gather to convert it. So author column, so you see it's Jim Austin. H.G. Wells. Author and their word use and definitely some frequency. Blah blah blah. So word 1, word 2, word 1, word 2, and map onto your corresponding frequency. And now we can definitely map that ggplot. So we use the y-axis for Jane Austen, or the upper x-axis as H.G. Wells. Right. So we use Jane Austen as a baseline. So for those words, they're not used by Jane Austen. They are the word used by H.G. Wells. Right? H.G. Wells. Then we can calculate the proportion. Yeah, we have already done so. Proportion for the total number of words used by Jane Austen. So for this, proportion is just W1 over W1 plus W2 is the total number of words used by Jane Austen. The fractions is calculated as a fraction of number of words in word 1 to all the words used by Jane Austen. Then we ask the ggplot to show this in a percentage format, then which is mapped onto a color gradient, so that high proportion should correspond to darker color, and they are closer to the main diagonal, the 45-degree regression line. So here I used the EV line, see, GG on EV line, right? You use a dash line, so the line type is 2. If you want to use a solid line, the line type is 1. Okay. So here it is. I use the slate gray and close to green, color gradient here. So map onto it. So for a word that's clustered around the 45-degree line, is also moving closer to if they are closer, positionally closer to the lower left bottom. That means those are the words that commonly used, mainly used by Jane Austen. See that it's most likely about like this word describing personality or woman's name. The person, or if a word that's off diagonal, they are more off on the 45-degree regression line, and closer to the top, to the say upper left. And those are the words that are commonly used by H.G. Wells. All right, so this very simple exposition of text mining is we actually not applying much statistics skill into it. So what about we now use some probability-based model to investigate the relationship between topic. Here I haven't talked about topic. I haven't used so far. We use the novel as a topic, right? So about the interrelationship between terms, document, and topic. So we can do that by using customer complaint data. They're complex. So see, what type of financial product were the US-based customer most likely to file a complaint about? Using the mixed membership probability generating model, LDA, latent derivative allocation. So to do that, we need the following package. And then we need to install often and load it. And here, the original data, if you found this online, is very large. It takes some time to download. So for pedagogical purpose, I just randomly pick the 10K example. The original data is about 100K, so it's only 1/10 of that. So I stored it in share Dropbox folder, so you can download. Then check out the dimension of that, right? It's just 10K data that contain 18 variables. So you can check out the name of data. So here, so you want to take a look at what type of tags are those complaints. So this is in the 6 column. This in column 6. See that many of them are actually empty tags, empty string. They don't contain any information. They're probably not just internet, like computer log or something. But for the third entry, you can see that. Right? He said, I submitted a complaint as PFSMO, CFFB, Consumer Protection Bureau or something like that. That did not respond to my complaint, blah, blah, blah. So I'm wondering if you can help me, or you can find the original copy of those documents so I can file additional complaint onto relevant agencies. Right. Of course, we do not want this extremely long column name, so we rename this column as text. Then we made it into typical format. It's easier to wrangle, right? So since we do not use line here, we use document. Alternatively, you can use document ID here. Since we're working on 10K data, so the observation would be 1 to 10K, right? 1 to 10,000. And the task that we will be working on to processing, stemming, and processing is the can found column 6 of the original data, so data is subset by text. So you will get us a 2-column table object. This is a document ID and text. So we will also load stop word and create our own stop word loads as usual. But here, if you look at the data, the original data, you'll find out that because you need to anonymize the original, the person who filed this complaint, right? For privacy protection. So they use a lot of scraps, right? It's just anonymity abbreviation. So we need to remove that because they would definitely appear quite a lot in our data, but they are meaningless for our analysis. So we should append those two terms under the stop word list. So this also offers instructional opportunity to show you if you want to also include your own stop word, which you think it will be better to get rid of on your data. Then you can also create a short list of stop word and then append on the existing stop word list. So I create a vector containing this to anonymity abbreviation, and also I create a data frame to concatenate with this vector of anonymity abbreviation. I said setting the row to 2 because only 2 of them, right? And then create a data frame. It has the label for the type of stop word, say, or. And also, the stop word itself, which is labeled as lexicon. So I create a data frame called anonymous. So I simply use rbind to bind into our existing stop word and create new stop word object called stop word. So I used to apply the same skill to parsing, stemming, and removing those stop words. And create a new data frame called text unmasking. And we generate then we also can count their word frequency and also sort them by the number of appearances in the data. And we can plot them. So again, we apply a filter here. So for all those smaller that appear less than 400 times, they will be discarded even though they were still the kid on the data, but they will now appear in your analysis. So we use 4 as the original x-axis, number of frequency, they appear as the y-axis, and then we flip that. So that it shows, the most commonly appearing word is credit, followed by account, report, information. Well, yeah, people want to ask information from the credit card company for the number of appearances. Right? And then to do that, now I would say most people who get interested in text mining are usually motivated by the word cloud picture that I saw on the news. They said, well, it's a really media savvy, you really want to learn it. And some people study text analysis just for the sake of being able to use word cloud. And I think that's really pathetic. Anyway, but here, there's definitely a very useful presentation skill, even though it is less useful for meaningful analysis, but we can still do that, right? So let's just talk about how to use word cloud. So again, use the object that just created a text count because we need the text, right? And the frequency of appearance in the data. We only need these two information to plot the word cloud. So here we count the number of appearance by applying the deploy count function and sort by the frequency so that the most frequently appear word will appear on top, right? In descending manner, followed by the second most frequently appear word. So now we create an object ready for word cloud presentation called text cloud. And then we call the library word cloud 2. We require word cloud 2 package. And then just apply the word cloud 2 function on the object just created, which consists of the word and their frequency sorted by their number of appearance. And let's quickly view the media savvy word cloud. So you can see the largest category is credit, right? Corresponds to this. If you click on the picture, it will show you the term and also how many times you appear, right? It wasn't very clear. It appeared like 137 times, right? But you say, wow, that looks really congested. Can I present less of it? Yes. You can control the number of words that are being projected onto the screen on the word cloud to make it sparser. Right? Or even say, that's not enough. I want it to be clockwise words. So you can actually make it denser by the number of terms you want it to appear on the screen. You can say, 100 isn't enough. I want 500, 1,000. Then I can do that. Also, you can say, I don't want it like square shape. I want it to be fancier. I want it a circle or a heart shape or sort of like star shape. And they actually offer this as a shape argument, so you can go online and find out the shape that you like. Right. So finally we get down to the LDA analysis. So in order to do that, we need the last object that was created. Text count create, so that include the text and the frequency of which they appear in the data. So we can cast that into a document term matrix that we're going to use for LDA analysis. So that means for each document, the frequency of the word appear in the document. So we just cast DTN. So you would create a DTN object, document term frequency matrix. And then we'll simply call LDA gplot2 and scale and snow function for parallel programming. Well, we probably don't need snow, it's for parallel processing. I forgot how to put it here. And the first thing you want to know is for, you already know the number of documents, right? It's 10K sample, working on a 10K sample. Number of words, but after you're applying on this pre-processing scale, you should know the number of token, number of words that you will be dealing with. But we don't know much about K, right? But of course, we can estimate that. So to do that, you will need a tuning package which contains a fine topic number. So, and then you just apply the function. Because it takes a lot of time depending on the size of the data. For this, it takes a couple hours. So I, just like this cooking channel, I already made that for you. So here you only need to download the result from a shared Dropbox folder, and then you apply the plotting function called find topic number plot, and then you close it. You close this result object, then you will find this for you. You see, I really provide 4 different matrices. The first 2 matrices are minimization functions, so that we need to find the number of topics that minimize this matrix. And that's considered to be the ideal number of topics. While the last 2 matrices of the maximization scale, meaning that okay, you need to find the number of topics that maximize this matrix, and they are considered to be the good number of topics. So simply find where this 4 topics cross. See, they're probably around here, like 14, 15, 16, around this, in this ballpark. Right? So that we can infer, okay, so probably this should be the ideal number K. And of course, there are different methods to do that. So there are many CAN packages that were plotted the perplexity analysis for you. Here, I also provide a more involved example here. Just don't do this at home. It take like 5 to 6 hours to complete because the involve a lot of training testing and simple speaking. So in order to do that, I have this my own hand-coded function. You will need a following package, and you already have this before, right? But to do this in a more sophisticated way, you will need to do some simulation, and there's a cross-validation. So we set out this parameter, the burn-in, the first set of data that are used for estimation, but will now be used for follower analysis, or need to be thrown out. And the iteration, also how many estimations to be kept. And then the DTN, we need to get the row latest of the DTN. And then we do trend test split, right? Iterate over 1,000 times, and we should apply a DA function, get fit value, and then do perplexity analysis on the trend data and validate it on tested data. And to do that, we need to have some parallel processing. So again, using the trick that I showed you previously, we leave one spare, right? So we register the rest of our computer core, CPU core on your current working console. So if you're working on a 4-core computer, you will use 3 of your CPU core. And then we simply throw all this parameter into this handwritten function. And after it's computed, you will stop this cluster and went back to the normal functioning, and then concatenate the result into a data frame, and then which you import it. Import the result using specifying the x as the number of k, and y is the perplexity score. Oh yeah, I already erased it anyway. But as I showed you previously, the perplexity the perplexity score is plotted as a decreasing function of the likelihood that your trend model is able to correctly shorten the topic of the word from the on-seek document. Right. So that the lower of this inverse likelihood, the better the model. But however, as the line begins to flatten or even begin to increase, that means that the additional number of topic, they cut down little and improving the model's prediction accuracy, so that we should stop. So you see that it's actually around here. And after that, the curve just flattened out. So we quite match, even though not exactly, to the previous find topic number function that we implemented previously. So if you want to do a more sophisticated, more involved analysis, you can consider using this code here. Right, so we link that to our previous analysis. So that previously we find out like this, any topic number between 14 to 16 are good. So we just take the average, just 15 topic LDA. Right. So to do that, here, it take quite some time. I don't want to waste your time. So if you want to do this analysis, just fit the DTN object into the LDA model. Remember that they are in capital letter. Right? This letter. And specify k equal 15 and set out the control function that set the randomcy to any number, any randomcy you like. Then you will generate an LDA object, which has already been created for you. You can download it from our shared Dropbox folder and check it out. So, okay, it's an LDA variational EM algorithm. The topic model with EM is variational EM algorithm, which is 15 topic. Right? It's very simple. And in order to show this mixed membership probability, you have to turn it back to the one topic per term per row format. And this can easily be done using the tidy function. Just use tidy and then apply it on the LDA object you just created, and then check this out. Right. So each row is a combination of topic and term with different probability, because each term, say even for the same term, consumer is related to the 015 topic that we assume, because we assume that k equals 15, right? So that each term has 15 probability, right? Term topic measure. We have 1, we have 2, we have 3, we have 15 of relating to each of this 15 topic. And this, which I show you here. And if you want to take a look at it, so one the top 10 most likely term for each topic, if you want to take a look at, then you can simply apply this function. By group by topic, we want to look at the most frequently appeared topic, the top 10 frequently appeared topic for each, for most frequently appeared term for each topic. So group by topic and filter by top 10. Based on the beta, right? The beta means the probability that is related to the topic. Based on beta, so higher beta means that the term is most likely associated with a particular topic. And then arranged by topic by beta, right? It means that in descending order. So you can check this out. Of course, there's one thing that you don't know. I actually don't know what topic 1. Which topic is topic 1? Well, you'll get to that later, real quick. So after that, okay, so we already checked out the term topic distribution. So what about topic document? Another important part of our analysis. Then you can just apply tidy function on the original LDA class object by applying the matrix code gamma. Remember that gamma is actually the theta that in your original model. Because in different textbooks, they actually use different symbol or different letter for the same thing. But here I keep using the theta, but here they use gamma. So you send a matrix argument to gamma, then they will return a topic document matrix for you. So that each document, each document is actually related to, is associated with different topic, right? So the measure the topic distribution in a document. And each topic may be each document may be related to different topic with different probability. With here is regulated by gamma. The higher the probability, the more likely that the document is associated with the topic. Then we can also visualize the term topic distribution. So here is very simple. We just apply this using a tiny function on the original LDA class object using the matrix beta, which will calculate the term topic distribution, and this return as an object. It would be a tiny object that represent a term topic distribution. Term topic, so you see that each term is associated with a different topic that is made of that. The probability that it is likely to be of this topic. And you can definitely display that. So using the top n function to find the top term within each topic is just directly applied as in the previous. Then we can also plot it. We're simply using the term as our x-axis, using the beta, using the probability that the term is related to a particular topic. And then sort this by topic, right? So using the phasor graph means that you will create the number of subplot corresponding to the number of this parameter. Here we use topics, and we have 15 topics, so you will create 15 subplot. And also to show this, to project the the top 10 term on the vertical axis, y-axis, means that we need to flip our original coordinates, so we apply coordinate flip. So we'll get the graphical output that contains 50 subplot, where the top 10 term for each topic are on the y-axis, vertical axis, and their probability of appearing, the probability that they are related or they are associated with this topic is mapped on the x or horizontal axis. Okay. So do you find anything insightful regarding this? For example, like, well, it seems like credit appear everywhere, it's just don't jump around everywhere. But mortgage is only appear in topic number 8, or debt is in topic number 7, and 10, probably something about car, vehicle, car, probably car mortgage, or car related credit, financial payment, something like that, right? So one way to test that is since the original data have several columns, it has the complaint and also the type of financial product in which the customer self-identify their complaint to be related to the type of financial product. So we can use that as our, say, the true value, right? And using the topic document prediction here we get from the topic document matrix that we get from LDA as our predicted topic, predicted financial product category. So we can actually merge them together to see to what extent do they agree with each other. They using a percentage of agreement between this row, this document, this row-based data, as an indicator for prediction accuracy of our LDM model. But of course, 15 category would be a little too much. You probably wouldn't get the accuracy from doing that because
or I think, to do my own perspective, any number category larger than 3 will be really hard to get satisfactory prediction accuracy. So let's just reduce that to 7. So here we need a function called recall. So here is the data, or is the column, the variable that we want to recall with. So in this category, because product is the financial product category, is a categorical factor-based data. So for value that contain this, they will be recoded to account. Something related to your bank account. Else means that other will retain their original coding. So here we actually merge two of the data into one type. So essentially, the first step we actually the number category is -1, reduced by 1. So in number 1, so we can continue to do that. For example, customer loan, payday loans, something about loan. They will collapse into one single category called loan. Others retain their original coding. Or the credit card is the same. Anything that contains they will be recoded to a credit card. Okay. And so for here, something related to, so long as this text string this category appear in original data, they will be recoded. We collapse into a single category called credit reporting. Others retain the same. So money transfer, currency, money service, anything related to money, they will be collapsed into one single category called money transfer. Others retain the same. So now we have collapsed the original 50 category data into a 7 category data. So we can use the table or table function to check out the distribution of different type of outcome. So our document, our text document, can only come from any one of these 7 outcomes. There's 7 categories. So again, we need to rename the 6th column as text, and then we subset the data. We only need the original completing text and their product category, which will serve as our true label. And then we preprocess the text using honest token to parsing it into its constituent word and removing the punctuation, stop word, space, using anti-join stop word, and then so count the sort, the frequency, and this should give you a glimpse in how was the most frequently appearing word on each financial product category and their frequency. So again, credit is the most frequently appear token. And of course, because credit appeared a lot, credit appeared in all the product categories. So you might want to refer back to one skill that I introduced an hour ago about TFID, term frequency inverse document frequency. So we need to adjust that so only those tabs that appear a lot in a given in a particular topic, but not anywhere else. Their probability, or so they are more related to that topic or category, but not others. So we need to adjust by TF-IDF. So how to do that? So should I write a function on it? No, you did not. We just apply the blind TF-IDF function, and again sorted by word frequency. And if you want to look at that in descending order, just apply the arrange that in descending order TF-IDF. Because the original scale is in ascending order version, so you need to reverse that in descending order. And showing the top 100 term to see what topic are they related to. To see that word Coinbase, right? This word related to money transfer. The expert is probably the U.S. Attorney General who legislate law on mortgage on the 2007-2008 financial crisis. So you can also see there the TF-IDF score and the resulting TF-IDF, which is just the multiplication product of these two, and their word frequency. So they have to be inverted frequency. Okay? You can also plot it. So simply plot the word frequency by topic according to TF-ID of school. So you just group by product, showing the top 10 frequency and using the matrix TF-ID of score on the y-axis. So here we could do that. So you create a 7 product because previously we have merged, we have collabed the original 15 category data frame into a 7 category data. Okay, so you use face red by product, you would generate graphical output that contain all these seven softball, showing the top 10 terms associated with that product category and the TF-ID score, arranged by the TF-ID score. So do you find any useful pattern? So I'll let you to decide. So eventually, so finally, you want to do a bit of prediction analysis, showing the prediction accuracy. So to do that, we need to cast that once again, into document term matrix. So again, it's by product and word, and arranged by the frequency at which they appear. So since now we have a 7 category, so we need to do LDA. We fit our DDN product into LDA function, and set K to 7 because it's 7 category. Each document can only count from the 7th category. I set a random C, so that generates LDA product. Since it takes a lot of time, so I set it into the Dropbox folder. You can directly download the result from the Dropbox folder. And we use group package to connect the LDA object, the original LDA object that contains all the parameters for LDA estimation with our new DDN object, with our existing DDN object, document term matrix. So you see that before. So the last thing, the output contains the original document label, right, and the term that's associated with those documents and their frequency count. Also, our predicted outcome, right? So the last task that we need to do to figure out how good our LDA model at predicting or at recovering the most likely topic for a piece of text is to figure out what those topic number is. Right? And this can be easily done by calling the topic document matrix, the distribution topic in a document, which is regulated by theta, but here they use gamma, right? So we just use tiny function to wrap around our LDA object and set the matrix to gamma. And then the first column, since it does not give it the good answer, we just name it as a problem. So that's LDA estimation for the probability that that the document is related to a topic at this probability. Right? So the document can, so since we're working in the 7 category data, so that the document can at most related to 7 categories with non-zero probability. So here we only want to get the most likely probability that this document is related to a certain topic. And this can be easily done by simply picking the highest gamma as the most likely topic. So we can just use sort function, use sort product classification result, and fit in this object they just generated and group by product and find out the top 1 gamma. The largest gamma means that the product is most likely associated with which topic. And then arrange the gamma, so showing the product classification. Okay, so this recovered the connection between the topic label estimated from LDA and also the predicted product category. So like topic 7 is most likely about money transfer, topic 1 is most likely about loan. And this, the gamma value no longer important to you because we already have this information. So what should we do right now? You just merge this predicted outcome to the true outcome to the original data frame. That can easily done by using either join, which I just showed you, right, by topic. Then we can check this out, showing the top, showing the top 10 row. Right, the document, this one. So showing that, okay, this is the true label, the original label of the data, and here's our predicted label. Well, not bad, right? But of course, here I only show the first 10 rows. We won't see that, so how good our model is at classifying the entire, all the document to their, in the appropriate category in the entire data set. So we can plot this out, right? So again, we count the predicted, the number of correctly predicted instance for each document category. And we want to get a percentage value so that for each of the document, right, it's mapped onto multiple topics. And we want to see to what extent are predicted the fate of that agree with the true label in the data. Right? So for each document, we'll see what the percentage of predicted value are the same as the true label. So here we generate one additional percent, which is just showing percentage term is the number of correct prediction instance over the total instance of the document. Then we use the x-axis as the predicted and y-axis as the original, the actual financial product category, the field by percentage, and we use the gradient color in red color to fill that. So now the darker is more red, means that the actual value, predicted value have higher agreement, means that our prediction is more correct. If you have a lighter color, that means that prediction is not so good. Okay, so we map this. We also arrange the angle of the text. We show 90-degree vertical text. We also create a label. Right, since the horizontal axis is our predicted value, vertical axis is the actual value. We also give a name to our legend, so the percentage of agreement. So it's not bad. They most agree with each other in the credit reporting, probably using the term they are highly specific. They are less correct in classifying money transfer. But here, it seems that you had done a relatively decent job for a classification test. So we're going to take 10 minutes break. After that, we will finish out the sentiment analysis. All right, so jump to the second part of this lecture. A related analytic approach to sentiment analysis, because not only can we infer the associated topic and content and the distribution across documents, but we can also infer the emotion of the author when he or she created those texts. And for that, we need to rely on sentiment analysis to infer this encoded message. For example, when you see a text that's, for example, about college matriculation being accepted into the prestigious college then you might feel happy, right? And also, if you read the really sad news about the tragedy of traffic accident, you might feel anxious or sad, right? So we can actually tell this from the test data that we create through our analysis. For example, here I used some example that I did in the past year. So the panel on the left is a collection of over 50,000 political blog data that was retrieved from this political blog, US-based political blog recorded between 2008 and 2009. So that happened during the first Obama presidential campaign. So we group them into different topics, right? So you can see that okay, for each topic related to different thing, right? The topic 19 is about Hillary Clinton, and the topic 18 about John McCain. Those are the compete for the Republican presidential primary. Right? Also, topic 7 is actually the vice presidential opponent for candidate John McCain. Also, topic 12, the ongoing Iraq war, right? And topic 15 about terrorist attack, probably in the Middle East, because they also the high frequency terror also include history. So each of the topics are associated with their corresponding unique term. On the other hand, there are we can also apply the same scale on Chinese text data. So here's the data that I retrieved on the Chinese Weibo, essentially the Chinese version of Facebook or Twitter. That retrieved at the height of Taiwan's 2018 91 election, 2018 general election. So that the copy of the highest proportion at that time is 91 election. Followed by KMT or something about Americans, always related to America. And also, we also identify topics related to the same-sex equalization referendum, same-sex marriage referendum, right? And also about the devastating outcome of the election, meaning that the DPP lost cavity and forcing President Tsai Ing-wen to resignate on her position as party chairman. But the most important thing is that they are there are some emotion behind this different topic. So you see that in the first topic, probably there is something about some joyful or happy expression among Chinese internet citizens regarding the outcome of the election. But we are also uncertain about, say, the topic 5. We don't say the same-sex marriage referendum, but we do not know how Chinese have to think about the same-sex issue. And to do that, this will require some text analysis skill and to retrieve sentiment underlying those texts. So how do we do that? How do we infer the sentiment from text? I mean, intuitively, if you are given the set of data, you can easily tell. For example, the customer complaint data says the first ticket is terrible customer service. That means that the writer of this text probably are expressing some negative sentiment at the moment. But terrific means that it's a positive tone, right? But what about ticket number 5, ticket number 6? So this cell area is probably is really angry, so we can clearly classify it as a negative sentiment. But here, now the bar cloud, the transitional phase, say, a word run separating two chapters, literature to describe a movie or a novel. It's a relatively good, but it's too sweet in that it's very unreal. So what does the yeah do on the judgment of the tone, the positive negative tone of this text? We don't know. Right? It probably means that the tone probably experiences some transition. So in sentiment analysis, we simply that's very simple. We just write a loop to identify a term belonging to positive and negative sentiment based on some predefined sentiment dictionary. So it's good if you have your own specified dictionary. That's good. But even better is someone really down that for you. So in our implementation, we just need to download those predefined dictionary and load into the data, and then R will match those predefined negative sentiment term on your text data, and then sum out their total frequency, and then get a net sentiment by subtracting negative count from positive count. And that's how they do that. So that is how they evaluate the rating. The rating statement can be either on the binary coding so long as the positive is larger, the sum total number of positive is larger than the total number of negative tone. That means, so we're simply call it as positive to make a judgment on the tone, on the sentiment of the text. So positive. If it's less than that, then it's negative, so we call it 0. Or it can be measured on a grading scale. So in text, it may contain lots of positive word, positive sentiment word. Over just a small meager amount of negative sentiment tone, then we say that the piece of text is very positive, so if you measure that on a grading scale. On the other hand, if the positive is only more than the total number of negative tone by just 1, then we say, okay, it's probably negative. But the probably, we say overall, the piece of text is very positive, but not by very much. It's a slightly positive. Great statement. So now here we're going to say something about this bar class, the transition phrase. So the common usage is that, so long as this type of term appears, means that the tone experiences some transition. How transition from negative to positive to negative. So how can we do that? It's simply just raise it to the power of 1 minus the total sum of both, right? So that if it's originally negative, and then in one of the paragraph you find out this block class, then you will be raised to the second power of that, right? So that the original negative tone be raised to the second power, become positive, so they experience some transition. But I would say this isn't a very precise way to do that, so I wouldn't recommend you to use block class to calculate the net sentiment. So we can actually, so for this type of data, we can actually map each of this top 10 topic on the positive and negative sentiment scale by using some predefined sentiment dictionary to rate those high frequency terms under those topics, and then calculate the net sentiment scale for those topics at aggregate level. So here, actually, you review much more information than we would otherwise know by simply looking at the distribution of topic stadiums. For example, you see that, okay, so for the first topic in elections, okay, so the Chinese stance actually expressed some positive attitude to positive sentiment to it because, well, the independence point DPF lost that election, right? But Also, they also express a negative tone toward a DPP. That is for sure, right? But what's really interesting is that they actually review more negative tone toward the KMT than to DPP, toward the unification from DPP than KMT than to DPP. That's probably something that the KMT should worry about, right? What's also interesting is that, well, they actually review positive tone towards same-sex marriage referendum. That's unthinkable. Also, regarding the procedure democracy, the formal definition of democracy, regarding the voting or the hearing procedure, it seems that they also held a relative more positive tone, even though only slightly, toward democracy than what the Taiwanese media will portray their procedure. They usually say, oh no, Chinese is an anti-democracy, they don't like democracy. No, it's probably not true, based on the sentiment rating. It's slightly, they actually hold a more slightly positive attitude toward democracy. Right, so we jump through our exercise. Before that, we'll do a quick review. So each variable is a column, right? So the variable could be document level information. So that's an ID, total number, item, order, and sentiment. Each observation is a row, usually it's a document, right? So it could be a string of text, that's the basic constitution unit of a document. A news report, legal document. While each row is a token. A token is mean for given a text, such as a word. And we can use apply many text processing tool for rainbow as well as text data. And again, I have to emphasize that usually text data are stored as text string, character vector. They are, especially the first thing, this is when they are first read into R or Python. But this computer program cannot directly read the text. You have to annotate that with additional information, labeling with their ID, the term or token ID and the document ID for your programming language to calculate your joint probability and distribution. They cannot directly tell you, okay, this text is about election, this text is about COVID. No. Right, so what a corpus is just a collection of objects that contain raw string, a piece of text, annotated with additional metadata. So they have, say, document level data, for example, document ID, total number of terms, more than segment, and detail, for example, like the geolocation where this piece of data was uploaded, or even the user's name who wrote this piece of text. So then contain lots of information. You can actually concatenate it together and do some predictive modeling. Then document term nature is a spot method describing a collection of documents with one row for each document, one column for each term. Okay. Now we have this exercise. So we will finish the last piece of exercise on sentiment. So to do that, we need to download, we need to record the following package. And we use the object that we just created on our financial product customer complaint product, financial product customer complaint data, to remove those for parsing and stemming, unitization, remove stop work, to create a new data for follow processing for new data on the nested. And then we join that with the Microsoft Base Sentiment Dictionary using inner join method. So that you actually do not need to compile your own sentiment dictionary. There exist also. You can use Google Sentiment Dictionary, Microsoft Base Dictionary, or some more refined dictionary data that, for example, like the NTU, they also compile their own sentiment dictionary data for traditional Chinese book. Okay, so you just inner join so that the function will find those sentiment terms is along their data that are located on your data. if they find it, they were sorted. So okay, they find SAT for the particular word SAT, then is related to negative sentiment, right? So you would sort this term SAT from your document into a row. Also, there will count the total frequency of appearance in your total data. For word like happy, okay, so you'll count total frequency of appearance in your data and give it its own row and count its total frequency. So you'll find this. Okay, so for that, it's definitely something that you own someone, so it's negative tone. It appear like 13 times in your total data. Right? And then we can actually plot out the distribution. So we first group by sentiment. So we first generate a plot group by sentiment. The sentiment level to see what the top term related to the positive and negative sentiment used in your total corpus. And after that, we would do a more refined classification by financial product type. So we list the top 10 sentiment dictionary by positive and negative sentiment. Right? So we first plot. So we first arrange those words on the x-axis and then the frequency on the y-axis, and then we flip, right, on the flip. So it shows, okay, so that is most appear most frequently in negative sentiment, or correct, appear most frequently in positive sentiment. And now we can also arrange that into a word cloud format. So since I want to show you in a slightly more fancy way. Because, for example, some of you are doing some legal document or case or also the document analysis. So you might want to sort it by the outcome of the ruling, right? So you can rely on the word cloud package, not the word cloud 2. Use the word cloud package. Exactly the one that I like the most. I think this. Exactly, we have a better visualization result in word cloud 2. Just media setting word cloud. I take them like only this high frequency term to be grouped by outcome, or to be grouped by relevant category. So, for example, if you do legal study, you can say, what are those words related to ruling that found the accused to be guilty or not guilty. So you can replace negative with not guilty to replace positive with guilty. Then you can find those top terms that are associated, top emotional term or key terms associated with that. Right. But to do that, we need to call a word cloud package, reach2 package, and then because we need to use a cast function for that. So we simply cast word so it was sorted by their sentiment type, right? So you see that, okay? So there are two types of outcome, right? They sort this word by sentiment. So negative, positive sentiment, and they're also given as a mapping with different color. Also, their size are proportional to their frequency of their appearance. So this is very intuitive, straightforward. I love this. So now we want to create a TIBA object, which is a data-free compatible object that corresponds to the total number of observations. They contain the text and the product type. I also want to before further processing. So again, we generate TIBA object and we remove the stop word unless the processing stemming. And then after that, we group by product and sentiment, and connect those tokens, which we just separated. Because we need to remove those like punctuation, symbol, space, in order to fit into the sentiment analysis function. So that's why we need a clean, pure text, and then we connect them back so that the new text color are without those punctuation symbols. So meaning that they have to be parsed Right, so, and to do sentiment analysis is very easy. You just download sentiment analysis package. Well, there are probably over 100 packages out there, so I just use the simplest one. And you call a package, and then apply their and analyze sentiment function on the on the text column of the table data frame you just generated, and this will give you a sentiment analysis object, which I store in our shared Dropbox folder, and you can convert their prediction outcome to a new column as character to a new column, which you can use this new character, the value in this new column to map the frequency count in the following ggplot2 object. So essentially, we just fit the table data frame we created. We ask them to come, to sort by product, to count their sentiment, to sort the sentiment frequency. And then we arrange that into a 7 category. Remember that because we previously had collapsed the 50 category data into a 7 category data. And then we'll place the sentiment. There are only 2 types of sentiment, positive and negative, on the x-axis, and the number of frequency on the y-axis. But here we do not use coordinate flip, we just want to preset that because we only have 2 types of sentiment. And so field by sentiment, and so face array by product type, so that will create a graphical output containing 7 product types. And then we use the black and white plotting scheme. Okay, so this shows the frequency distribution of sentiment across financial product type. Okay, so that's all about it. So this is simply conclude our today's lecture. Great.